Section 14.2, the ideal gas law. First off, what does it mean for something to be an ideal gas? Well, this is an idealized model that works if you have a real gas with a sufficiently low density. So it's something that will assume basically all of our gases are ideal gases, but it does actually work in real life if you have the right conditions. So the condition of low density to make something behave, a real gas behave like an ideal gas, means that the molecules are so far apart that they don't interact, right? They aren't affecting each other, except when they're colliding with each other. And the collisions of gas molecules are effectively elastic. It's probably our best example of an elastic collision. So that means the gas molecules basically are totally independent of each other. Now, we could take some observations of how a gas behaves when we change various things. Like if we have our gas that's in water and we change the temperature, what would that do to the pressure? Well, we could measure that with a pressure gauge, right? And what we'd find is that as we increase the temperature, the pressure increases too. That the pressure is directly proportional to the temperature. So higher temperature means there's also going to be more pressure in the gas. All right, what other changes could we observe? Another change we can observe is what if we keep the temperature constant, but then increase or decrease the volume? What happens to the pressure of the gas then? Well, we find that as we decrease the volume, if we compress it, we actually get an increase in pressure. There's less space for the gas molecules to bounce around, and so the pressure goes up. And that's what's shown here, right? That as following what's known as an isotherm, this is a line of constant temperature. So as we shrink our volume, right, volume goes from this large value to a smaller value, the pressure goes from a relatively small value up to a higher value. Finally, the pressure, it turns out, is proportional to the amount of gas. So if we have more gas in the same container at the same temperature, it's going to be a higher pressure, right? We can keep adding more molecules in there, and that's going to increase the pressure. So if we take all three of these ideas and put them together, we get something known as the ideal gas law. Something you may have heard about, right? Especially if you've taken chemistry. Says that the absolute pressure of an ideal gas is directly proportional to the Kelvin temperature and the number of moles of the gas, and is inversely proportional to the volume of the gas. So that's written here with P is equal to number of moles N times R times T divided by V. Or the more common way that's often written is PV equals nRT, PivNert, if you will. So this is a key equation, right? A couple of notes here, right? Little n is the number of moles. T is the Kelvin temperature, so that must be in Kelvin. And then there's this R as well. R is known as the Rydberg constant, so that's something that is included on your the sheet that you get with an exam. That's 8.31 joules per mole per Kelvin. And that's the clue that your temperature needs to be in Kelvin in order for that to cancel out properly. So with this ideal gas law, you can learn a whole lot of different things. But in some problems, we aren't working with a number of moles, right? Sometimes we don't have moles given to us. It's a number of molecules or a number of atoms. If we were dealing with a number of molecules or a number of atoms, that's where instead of using this little n, we're going to want to use our capital N, big N. So we remember that little n, number of moles, is equal to the number of atoms or number of molecules divided by Avogadro's number. So we can fill that in here for the number of moles. And then we're going to regroup the Rydberg constant divided by Avogadro's number, R divided by Na. We're going to make this a new constant known as the Boltzmann constant K. So the Boltzmann constant K is equal to just the Rydberg constant divided by Avogadro's number, 8.31 divided by 6.022 times 10 to the positive 23rd. And as a result, since we're dividing by a really big number, the Boltzmann constant is a really, really small number. So this is another one that is given to you on the conversion factor sheet, but you have to know what it is because it's just labeled with a K. And we've already seen K can also be thermal conductivity, for instance. I know, again, we don't have enough letters, and I'm sorry for that. But here we have that 1.38 times 10 to the minus 23rd joules per Kelvin. And that allows us to then write the ideal gas law in terms of the number of atoms or the number of molecules, right? So that's the other way we can write the ideal gas law. It's not just piv inert, but it's also PV equals capital N KT. So that is another useful form of our ideal gas law. Let's check out an example of this in action. So one cool example that is very near and dear to each of us, unless you're a robot, is oxygen in the lungs. So in the lungs, the respiratory membrane separates tiny sacs of air at a pressure of 1 times 10 to the 5th pascals from the blood in the capillaries. These sacs are called alveoli. The average radius of the alveoli is 0.125 millimeters, and the air inside contains 14% oxygen. Assuming that the air behaves as an ideal gas at 310 Kelvin, find the number of oxygen molecules in one of these sacs. So this is something I didn't know much about. I still don't. Some of you probably could teach me much more about this. But this is how your body takes oxygen in, right? When you take in a breath of oxygen, that oxygen goes into the alveoli, right? And that then sends it into the bloodstream. And these little sacs then take the carbon dioxide out of the bloodstream, and that's what you then exhale out, the waste byproduct of the whole process. So these are at the heart of our breathing. Super cool. All right, so anyways, all that aside, what are we trying to figure out here? It says we want to try and find the number of oxygen molecules. So this is where identifying the proper variable can be really useful. If we want to find the number of oxygen molecules, anytime it says number and it's not number of moles, that's going to be our capital N. So number of molecules, number of atoms is capital N. So that is what we want here. All right, do we have any other clues to help us out? Well, let's see. We have the pressure. That's handy, right? Remember those pascals that we saw back in the fluids chapter? So cool, we have pressure. And we have that the air is 14% oxygen. Okay. So that's just a percentage. And then finally, we also have the average radius. Okay. So we have the radius. We want to find the number of molecules. Oh, and finally, we have this 310 Kelvin. That's great. Because what is that? That's our temperature. So I'm noticing we have pressure and temperature. We want to find N. This is looking like our ideal gas law with the NTK version, or NKT. So PV equals capital N KT. In other words, we can find the total number of molecules in the sac if we take our pressure and multiply by our volume, and then divide by the Boltzmann constant and the temperature. So let's check. We know our pressure, we know our temperature, we know the Boltzmann constant, that's just always the same. What about this volume? Do we know anything with the volume? Well, we do know the radius on average. And these tiny sacs, it doesn't specify their shape, but since it specifies a radius, that sounds to me like we can assume that these are approximately spherical. That's a common thing with physicists, is we like to make things spherical as much as possible. All right, so there's our sphere with a radius r. Since it's spherical, how can we figure out the volume? Well, that's the volume of a sphere, right? Volume of a sphere is going to be 4/3 pi r cubed. All right. So with those pieces, that will then allow us to solve for n. But we do have to be careful here because we don't want to find just any n, but we want to find the number of oxygen molecules, the number specifically of oxygen. And the air inside is not pure oxygen. It's only 14% oxygen. So when we get this n, it's going to be all of the air. So if we want the n of just the oxygen, we're going to have to take the n of all the air and multiply by that 14%, or by 0.14, to see how much of the air is actually just oxygen. Right, so this is a pretty good overview of where we're headed. So let's take a look. Okay, so n, the number of molecules of air, is equal to PV divided by KT. So we have the pressure times the volume, which notice this volume is 4/3 pi times that radius converted into meters. So 0.125 times 10 to the minus third, as opposed to being millimeters. And then that's cubed, can't forget the cubed there. Divided by the Boltzmann constant, divided by 310 Kelvin. And so that comes out to 1.9 times 10 to the 14 molecules of air in this tiny volume. So then the number of molecules of oxygen in one of these tiny sacs is just that 0.14 times 1.9 times 10 to the 14. So it comes out to 2.7 times 10 to the 13 molecules of oxygen. All right, so that is a ton of molecules because they are very small. But that's how much work your lungs are able to do thanks to these tiny little sacs. Pretty nifty. All right, one more example, a conceptual example of beer bubbles on the rise. If you watch the bubbles rise in a tall glass of beer and look carefully, you'll see them grow in size as they move upward, often doubling in volume by the time they reach the surface. So why does the bubble grow as it ascends? Is it A, because of the Kelvin temperature, B, because of the absolute pressure, or C, the number of moles, N? So I want you to think about this, come up with an answer before you move on. So go ahead and pause the video now. All right, hoping you did that. Okay, well, let's look at the different possibilities here. Kelvin temperature, that would mean that in order to get the volume to grow, if we think of our PV equals nRT, right? Ideal gas law. So if we want our volume to grow, that means we would have to have our temperature, to have the volume double, we'd have to have our temperature double, the Kelvin temperature double. So it'd have to go from, maybe 300 Kelvin to 600 Kelvin, which at that point, there's no beer left. So we're not going to be able to get that with the Kelvin temperature. What about with the pressure? Well, one thing that could come up here is that it's true that the pressure is greater near the bottom, right? We saw that as you go deeper in a static fluid, it's a higher pressure. So as you rise, there's going to be less pressure. But is that change in pressure going to give you a factor of 2 for the volume? It turns out not so much. You can do the calculation. You can treat your beer like water, for instance. And the difference in pressure, assuming you don't have a beer glass that's a skyscraper, the difference in pressure is not going to be anywhere near big enough for the bubble to double in volume. So what do we have left then? The number of moles. How could the number of moles increase? Well, think of the bubble, and as that bubble drifts upward, it bumps into other carbon dioxide molecules, right? And then it can actually take more gas in. And that's what increases the volume, is that we're getting a huge increase in the number of carbon dioxide in the gas form. And that makes the bubble bigger and bigger as it rises to the surface. So this is one example where N is not constant, where we have a changing number of moles. We will also see a number of examples where N is constant, where it's held in a fixed container. So that's a good contrast to draw here. If we consider a sample of ideal gas that's taken from an initial state to a final state with the amount of gas remaining constant, with no exchange between any other environment, then we note that with our PV equals nRT, we could solve for nR, and nR would be a constant here. That would be not changing, whether it's in the initial state or the final state. If something's equal to a constant, that means everything else, the PV over T, must be conserved. As the pressure times the volume divided by the temperature at the initial state must be equal to the pressure times volume divided by temperature in the final state. That's what this equation says. And this is a really handy one because there are a number of instances where we do keep the amount of gas constant. It's just in a sealed container for the entire duration. All right. So this is a good one to keep in mind. I'd say this is one of the better uses of the ideal gas law, is when you have constant number of moles, and please include this when you write this equation in your crib sheet. You have to know when to use this. But if the amount of gas remains constant, then this ratio must also remain constant. We could then look at some subcases of this, right? If in addition to having a constant amount of gas, we also have a constant temperature, well, then the initial temperature will be equal to the final temperature. So that will cancel out of the equation. And that's how we get what's known as Boyle's law. This only applies in the instance of constant temperature and constant N. So please, again, be very clear when you write this equation out of when you can use it and when you cannot. It's safer to assume the top equation and then discover that a lower one applies. Finally, there is, if it is constant pressure along with a constant amount of gas, then the pressure would cancel out and we'd be left with volume divided by temperature. This is known as Charles' law, but again, very rigid constraints on when we can use it. So this gives you some different approaches you can use, and it clues you into things that you should be looking for in a problem. If a problem mentions that the process is done at constant temperature or constant pressure, that's when you start going, ooh, that's a clue that something's going on here, right? Or if it doesn't mention any gas being added or removed, that's a clue that most likely the amount of gas is constant. All right, so this all introduces the ideal gas law.